Hello again and welcome. Today I'd like to talk a little bit about how to protect your NanoVNA. I'm sure a few of you are aware that I'm currently in the process of porting my software for the V2 Plus 4 to support the original NanoVNA. And like the V2 Plus, that software would also be publicly available. One of my concerns with releasing that software is that there were several flavors of firmware for this original Nano. Even the firmware that's installed in this particular Nano, it has a lot of bugs. So I started going through the forums to try to figure out, is there a stable version of firmware for this original Nano? And one of the things that I kept coming across is where people were blowing their Nanos up. The stories seem to follow a common theme. It's typically an amateur radio operator. They want to connect this thing up to their antenna system, so they hook it up and they realize that they've damaged their Nano. So the first case I'd like to talk about is they have some kind of a radio transmitter and they'll hook this thing directly up to the Nano. Really. And you know, however much power this is putting out, let's say it's 40 watts or 5 watts, you know, the Nano isn't going to be able to handle that kind of power, and of course it smokes it. You would expect that. I don't know why anybody would do this. It's interesting because I've purchased a lot of used test equipment for my home use, and a lot of that is used for RF work. And in some cases, the test equipment's front end will be blown. Many times this test equipment was originally very expensive, so you can just imagine that some guy is trying to, for example, characterize an amplifier on a network analyzer, and they hook this thing between port 1 and 2, and there's no attenuators or anything, and before they know it, they're putting 100 watts into their VNA's front end, and they smoke it, and then they don't understand why. Now, it may be possible to protect the Nano from this kind of condition. I don't know, we'll have to think about it. A more common one is they'll have an antenna, and that antenna is sitting up on a pole, and they'll, sounds like, climb up the tower and they'll hook up their NanoVNA up here and try to measure this antenna directly, and essentially it damages the Nano. So then there's another group of people, and here they have this transmission line feeding the antenna, and that transmission line goes down into their shack and they connect the Nano down here, and again, as soon as they do it, they take out the Nano. So a couple of things about this kind of configuration. Let's say they're feeding this thing with RG8U, and I think that has a capacitance of 30 picofarads roughly per foot. So let's say that's a 50-foot run. Well, that's 1.5 nanofarads. What can happen is, again, this antenna sitting up in the air like this can build up a static charge. Of course, that can charge this piece of coax. And I don't know, that coax will probably break down, let's say 4,000 volts or something at the end of the connector. So you have this 1.5 nanofarad capacitor charged to 4 kilovolts, and then you attach that to your Nano and you don't think it's going to damage it. Yeah, okay, so could you protect against this? Maybe. A couple of things that you could do in all these cases. The first thing you could do with this is bleed off any charge before you hook the Nano up. So essentially just ground the end of the connector and then attach the Nano. So all you really want to do is just ground the end of this cable before you attach it to the Nano. You know, here, again, we're working on a ESD type mat. So this is grounded back to the earth ground, and that's how I bleed off any static here in the lab. And of course, I frequently use a wrist strap when I'm working on equipment here as well, because a lot of the stuff I work on is ESD sensitive. So the same thing for the person climbing up the tower here. All they really need to do is make sure that they ground out that antenna. Now, there's also people that will hook up the Nano, apparently, to this antenna, and they'll leave it there overnight, for example, come in the next day and the thing will be damaged. That's kind of an odd case because, you know, the input impedance of the Nano is 50 ohms, so I would expect that to actually bleed off any charge that's getting built up. Probably more what happened is they had the thing hooked up and they damaged it right then and there. The other thing you could do is insert something like this. This is made by Cytel. This contains a gas discharge tube. You just remove the screw and you can replace that. So this goes in line with the coax, and you'll have a piece of braid, and this will go back to your earth ground. And again, the idea is that this gas discharge tube could have, let's say, a breakdown voltage of 500 volts, for example. And so if that charge gets above that, this gas discharge tube will fire and essentially bleed off that charge to ground. So let me just talk about that a little bit. A gas discharge tube, it literally is a tube filled with some kind of gas. It was even pretty common to use neon bulbs for transient protection. So anyway, you can buy these tubes, and they have different shapes and sizes, and they'll have different ratings on them for voltage breakdown as well as the amount of energy they can dissipate. Essentially what ends up happening is the voltage with this, as it climbs up to whatever the breakdown is, this thing will start to conduct, it breaks over, and essentially it becomes a dead short. So once these fire, it's a very low impedance path. Unlike, for example, if we had a diode in here, or say a set of diodes back to back, let's say these are silicon, so instead if the voltage comes up, we hit this 1.2 volts or so, and that's where it clamps it to. So there's a disadvantage to using something like a gas discharge. One of the big problems is that they're very slow compared to a modern diode. But on the plus side, they also have a very low capacitance. Some of the modern TVSs that are used for communications can have capacitance well below 1 picofarad. So they're on par with something like this, plus they're very fast. The problem with using the TVS is it may not be able to dissipate the kind of energy that we're talking about. So let's talk a little bit about static discharge. This is a small gas grill igniter. I made a video where I characterized this grill starter, and I compared that against the IEC standards, and this thing is quite impotent actually. If you look at a standard Esd discharge, it kind of looks something like this. So when you're normally testing this, you're pointing this at what's called a target, and essentially it's going to be a disc. And this will have a very low impedance to ground, and then we'll hook this up to some length of coax, and that'll go back to a high-speed oscilloscope, and then we can look at the waveform directly. So if you're interested in seeing how that's done, I'll just provide a link in the description. Of course, this grill starter actually damaged quite a few multimeters. A lot of people were complaining that, you know, this was too severe of a test, and so I had built a larger transient generator. So this generator pretty much follows the IEC standard. So again, I can attach up my device that I want to test to the ports here, and I manually trigger this up with a button on the side, and I have to flip the leads to do both positive and negative transients. The problem with using that generator is I'm using the human body model. Essentially what you end up with is a capacitor with some source impedance, and then this is again going off to our device under test. So I charge this thing up to some voltage, and then I discharge it through my device. It's not as simple as this. There's actually a network that's inside of this box to give us this particular wave shape. But to give you an idea how fast this transient is, we have to reach this peak in less than 1 nanosecond. I want to say it's sub 500 picoseconds actually. And the time for this total transient, I think it rings out pretty much around 5 nanoseconds. So it's a fairly fast transient. Now, when you're hooking up the nano to the backside of this 50-foot run of RG8U, you don't have any source impedance really. This goes away. This is essentially zero. And instead of, 100 picofarads or 150 picofarad, again, we're talking about 1.5 nanofarads in this case. Even testing the nano with something like this, that would be far less severe than our guy sitting here in his shack attaching his nano to the end of his coax hooked up to his antennas that are charged up. We're going to go ahead and run a quick experiment. Off to my left you can see I have our oscilloscope. This is currently set for 100 volts per division and 10 nanoseconds per division. This is attached to our high voltage probe. This probe is rated for a DC to 20 megahertz and can handle up to 65,000 volts peak. And then off to the right you can see I have our transient generator. Again, this transient generator can put out both the pulse as well as a DC voltage. So we're going to be using the DC voltage mode. In my hand I have a couple of different components. These are two different gas discharge tubes. You can see one's quite a bit larger than the other. This one is rated, I think, somewhere around 200 volts or something, maybe 160. And I also have a TVS. This is rated for somewhere around, I think, 130, 140 volts. Doesn't really matter. I just want to show you the difference of how these two parts behave. So what we're going to do is attach these directly across the oscilloscope. We'll start with our TVS. This is a unidirectional part. They do make them in bidirectional as well. Attached to the output of our high voltage generator, I just have a 2 mega ohm resistor to limit the current. So we have our variable power supply, our 2 mega ohm resistor, and our TVS diode. Let's just go ahead and start turning up the voltage. Again, this is 100 volts per division And you can see what's happening. I'm putting out 300 volts right now, and our diode is clamping. Again, let's just go ahead and remove the diode, and we'll just connect the transient generator directly to our oscilloscope through the 2 mega ohm resistor. And you can see we're putting out roughly 300 volts right now, and you can see we're just shy of 3 divisions up. So the diode is, of course, what's doing our clamping. So now let's try the same test with our gas discharge tube. Again, this component has roughly the same breakdown voltage. And just like before, we've got it directly across the oscilloscope probe. And now let's go ahead and turn up the voltage and see what happens. You can see how this thing comes up to about 200 volts, but something was happening right there. You can see how it's kind of pulsing. Let's go ahead and slow down our oscilloscope a little bit. Of course, it has to recalibrate. You can see it's basically oscillating. So the voltage rises up, the gas discharge tube fires, it essentially shorts out our power supply, and then the cycle begins again. So that's one of the differences. This gas discharge tube is a very low impedance path after it fires, but up till that point it's very high impedance. And again, the capacitance of these components is going to be very low, much better than what you would get with a standard silicon diode, for example. So in the first video I had made where I looked at this nano, one of the things I did was hook up a small transistor with some gain, and we were measuring the 3 dB compression point. Off the top of my head, I don't remember what that is, but to give you some idea of how much voltage this thing could actually handle on the front end, what we can do is look at the output signal. So this is currently just attached to the input of the oscilloscope. Currently I have a center frequency of 10 megahertz and a span of 2 megahertz, so it's scanning between 9 megahertz and 11 megahertz. And you can see the sweeping function here. Our current peak-to-peak amplitude is 250 millivolts or so. And just to be clear, the input impedance right now is 1 mega ohm. Normally this is going to be hooked to a 50 ohm system. Let's just go ahead and change that to 50 ohms. And we can see now our peak-to-peak voltage is reading roughly 130 millivolts or so. Of course, we don't want to have that clamp sitting right at that 130 millivolts. You'd like it to be a little bit higher. Basically, what we don't want to have happening is where this is working against whatever clamp we have on the output. And again, that's one of the advantages of using something like the small gas discharge tube, is this isn't going to present much of a load to this at all. I would imagine a few people have just taken a couple of back-to-back Schottky diodes. Again, the capacitance loading of those is fairly low. So what I'd like to do for this video is demonstrate a multi-stage clamp. So here again we'd have our antenna, our long stretch of coax, our ham operator sitting inside of his shack. He doesn't appear too happy because he just blew up his nano. What I'd like to do is have a device that he could just have attached to this nano all the time, and then when he just plugs it into the antenna he wouldn't have to be concerned. So what I'd like to do is have a gas discharge tube for the front stage. I've got some parts that'll fire I think as low as 60 volts. I'd like to follow that gas discharge tube with the TVS and then into the nano. Again, this gas discharge tube is going to be very slow, so what will happen is before this thing will fire, that transient's going to reach a very high voltage for a fairly long time, and then eventually this is going to shunt all that energy back to ground. But unfortunately the nano probably isn't going to survive that, so what we want is this TVS here to handle that short duration until this gas discharge tube is able to fire. Of course, if these are attached to each other, it's not really going to help because this TVS will fire before this gas discharge tube, and this may not be able to handle our poor amateur's 100-foot or whatever a coax he's got dangling off of this thing. So that's really what we want this gas discharge tube here for. So there needs to be something between these two. So really, ideally, we'd have some resistance there. In our case, what we're going to be doing is placing an attenuator in there. Now, again, to be clear, this video isn't on how to protect your receiver. The goal here is to try to protect the nano. So I'm not trying to receive, signals from across the world or anything with this. So I really don't care about giving up some of the signal. The question is how much signal can we give up? Again, this thing is driving a signal out. Again, we can see that with our scope. It's outputting a signal, and it's measuring that incidence as well as the reflected signal. and that's how it's doing the computation. So we could probably give up some of this output signal, and that would give our TVS something to work against. So what ends up happening is the voltage starts coming up, this guy will start to conduct, and all the voltage will be dropped across this attenuator stage up to the point where the gas discharge tube fires, and then again it yanks everything back to ground, taking the strain off of this and off of our attenuator. So what can we get away with for this attenuator? The Nano doesn't have a lot of dynamic range. So can we do 30 dB? 40, 50? Probably not. Could you do 3? Maybe. So I think that's the next question, is just what would be the right number for this? And part of that's going to be dependent on the frequency that we want to operate at. Of course, I've said that this Nano is basically only good for 300 megahertz. That's where I'd recommend using it for. So let's just assume that our unhappy amateur radio operator is operating somewhere between a megahertz and 300 megahertz. So here I have our original NanoVNA. Port 1 is attached to one side of our step attenuator. The other leg is attached to the through of our standard, and then the other side of the through attaches to port 2. Down here I have several standards. We have our 24.9 ohm. Again, that should give us a 2-to-1 SWR. We also have our 100 ohm, which should also give us a 2-to-1 SWR. And then I have a 200 ohm resistor, and this will give us a 4-to-1 SWR. I'm just assuming that our amateur radio operator isn't working much outside of 4-to-1 SWR. So this is looking at the software. If you watch my review of the V2 Plus, the software is very similar, and that's again because that software was essentially ported over to the original Nano. Currently I'm just testing this software. Once I'm comfortable with it, this is what I plan to release to the public domain. Let's just go ahead and we'll select link, and then we'll select sweep, and let's select transmission, and you can see we're currently measuring about 40 dB down, and currently the analyzer has not been calibrated. So let's go ahead and load up a 2-port calibration, and I'm just going to select this 1 megahertz to 300 megahertz. It's a 1-port SOLT cal, and you can see that changes our scaling from 1 meg to 300 meg, and it's loaded up now, and you can see we are at minus 30 dB. Again, that is what our step attenuator is set to. The inner dial set for 10 dB, and the outer set for 20, so 20 plus 10 gives us the 30. So what we're going to do is run through a SOLT calibration for 30, 20, 10, and 0 dB, and then we'll check some of these different loads and see what we get for an SWR. And I've already gone ahead and calibrated this unit. So let's just go ahead to 2-port cal, and again we'll select old, and we'll select 1 meg to 300 meg, 1-port SWR, 30 dB cal. And let's go ahead and select standing wave ratio, and you can see I have our 50 ohm load attached, and you can see our SWR is anywhere between, I don't know, 200 or so, as low, I just saw like a 2000 maybe, so it's all over the place. It looks fairly stable below about 150 megahertz. So let's just change our stop frequency to 150 meg. So you can see even between 1 and 150 megahertz, our SWR is still reading between, almost 4-to-1 down to 1-to-1. So it's got a lot of noise on it. Let's just save this off to memory 1. And now let's change our step attenuator to 20 dB. And we'll load up our 20 dB calibration. Again, we select old and SWR 20. So now look at how flat our data is. Even up at 300 megahertz, it looks like it's below about 1.3 to 1. Well, there's a high spike at about 1.6, but this is greatly improved. And again, let's just have a look at 150 megahertz and lower. You can see there we're all the way down to about 1.1 to 1 or so. So if you were going to operate at those lower frequencies, you might be able to get away with even 20 dB of attenuation. Let's try going down to 10. So again, we're just selecting our outer to 0 and the inner to 10. It gives us 10 dB of attenuation. And now let's load the 10 dB calibration. So SWR 10. Let's go ahead and clear out our 30 dB memory storage and have a look at this. So we're now as low as, 1-to-1 up to 1.02 to 1. So very acceptable. So I would say if we wanted to use about 10 dB of attenuation just for measuring SWR, that would be great. Again, I'm not suggesting that you would put a 10 dB attenuator in front of your receiver that you're trying to pick up signals with, but that's not what we're trying to do here. We're trying to measure an antenna's SWR and not damage the VNA. Let's just try our 25 ohm resistor. Again, this should give us a 2-to-1 SWR, and have a look. So 1.93 up to 2. So I would say very respectable. Let's try it with our 100 ohm resistor. Should give us the same SWR. Have a look at that, 2 to 2.1 maybe. Again, very good. That's all the way up to 300 megahertz. Let's just try it with our 200 ohm resistor. Again, this should be a 4-to-1 SWR. I'd say again, very reasonable. So even if you're operating up to 300 megahertz, I would say this is pretty good. So now we have an idea that even with 10 dB of attenuation between the nano and the antenna, we get acceptable data up to about 300 megahertz. So what I'm thinking to do is share this 10 dB attenuator between these two stages. So over here I have our unhappy ham hooking his coax up to our little protection device. Again, the first thing that the transient sees is this gas discharge tube. It goes through this first stage of attenuation, hits the TVS, goes through a second stage of attenuation, and then on to the nano. So a couple of things with this. If we build this out of 1206 devices, so that's a package size, these resistors can only dissipate about 1/8 of a watt. And they're good for roughly 200 volts is all. So a couple of things. If we use this type of attenuator versus something like this, because of this 200 volt breakdown, we may be better off with a T like this. But we said already that we're going to try to pick this gas discharge tube somewhere below 100 volts. So again, we're not talking about DC voltages normally. We're talking about a transient that's stored in this big piece of transmission line and up in our antenna. So if we use this type of attenuator, again, out here is our TVS, and let's just say this is, I don't know, 5 volts. So I put 2000 volts out here, and I've got a 24 ohm resistor. This basically handles the entire hit. Again, with that gas discharge tube in there, that part would probably survive quite a bit. But just a reminder, I'd said that one amateur operator had talked about hooking the nano directly to the output of his radio. I don't know why you would ever do that, but that's what happened. So now, you know, we've got this, I don't know, whatever, 100 watt radio out here, kilowatt, whatever it is, and that's hitting up against an 1/8 watt resistor. So what'll happen is that resistor is going to blow. It'll be a sacrificial part. It may actually even take out the GDT. Of course, it may damage his radio having that thing shorted. Depends on the radio probably. But the nano is going to be protected, because once this blows, hopefully even if this guy fails, whether it blows open or shorted, we'll have another attenuator stage on the back side of this. So it's almost like it's double protected. Again, this attenuator giving this TVS something to work against, and this attenuator dropping this thing from 5 volts down to something that the nano can handle. So if we were going to use a 3 dB attenuator on the front end, these two values will be 221 ohms, and then we'll use a 24.3. Again, the values for these are not very critical. We're not trying to build a very high fidelity attenuator. We're working below 300 megahertz. You can get away with quite a bit as far as the construction. So these are just common values. They'll get us pretty close to 3 dB. Good enough. Again, out here we have our TVS. And again, that's a bidirectional part. So the next thing what I'm thinking is we had a small capacitor here. If we use a ceramic part, these are typically going to be good for 50 volts. And the reason I'm going to put this on the back side here is I can get away with a smaller component. And I would like this thing large enough where the impedance of this at, say, a megahertz is low enough where it really doesn't impact our measurement. So if we use a 220 nanofarad ceramic capacitor at a megahertz, we're looking at an impedance of roughly 0.7, which again, that's going to be fine. We're talking about resistance values of 24 ohms or so. Adding an extra ohm for this is not going to be a big deal. Most people aren't going to run that low in frequency anyway. If you are, you could always pick a different value. Of course, this channel isn't really noted for a lot of hand-holding. My goal isn't to give you a circuit that you would just copy and build and, you know, hook it up to your nano and all is right with the world. You know, that's not the goal of this channel at all. What I'm trying to do is present some ideas that you could use to design your own transient protection that would work under your conditions and possibly save your nano. So it's a big difference. Not everybody is going to have, 50 or 100 foot of RG8U. A lot of people are smart enough to know that they need to short that coax before they hook it up to their equipment. At home here, beyond the 3 NanoVNAs that I own, the 2 pluses and then the 1 original nano, I have 3 other network analyzers. Those are all vintage HP equipment. All of those have very sensitive front ends. And of course, if you watch my review of the V2 Plus 4, you saw where I compared some data off of that against my latest Agilent network analyzer, and we were running all the way up to 4.4 gigahertz with that. So again, that network analyzer that I own, it's no slouch. It actually runs well beyond the 4 gigahertz, so but I take precautions when using that old equipment, and it survives a long life here. So again, getting back to our DC block, let's just say our amateur's antenna is just being used for receiving, and he has an LNA attached up on top of the tower, and so he's pumping DC up this line. So let's say he forgets about that DC, and he attaches that coax again back to his little nano, which isn't probably going to like that DC voltage hanging on it. Well, again, adding that capacitor, that's just going to give us a little added insurance to block any kind of DC, and again, prevent damaging the nano. So if this is a 3 dB attenuator, we're just going to set this for 7 dB. Looking at this TVS, what we'd like to do is get something, again, with a very low capacitance. We'd like something less than 1 picofarads. Again, a lot of the TVSs that are designed for high-speed communication, you'll see them less than 1/10 of a puff. I would just go to a DigiKey, for example, and start looking up TVSs. Again, trying to find something with a low enough capacitance for whatever range you're working with. Again, if you're working in, let's say 10 megahertz and lower, you could get away with a much larger capacitance. Of course, in that case, you may be able to actually get away with a couple of Schottky diodes. It just depends what your circumstances are. I would pick whatever clamping voltage you need to work with whatever attenuator that you came up with here. I would just keep in mind that this nano is capable of putting out about 260 millivolts, so you probably don't want to exceed whatever the supply rails are for the front end. I'd say as long as you're not doing that, you're probably going to be okay. So I would work backwards from that, pick whatever clamp you need, and then again, try to keep your gas discharge tube somewhere below 100 volts if you can. Again, it just takes the stress off of this stage and off of the TVS, and you should be good to go. So this is the suppressor that I came up with. Again, this is strictly used for measuring SWR. This would not be good to make any other kind of measurement with the nano, again, because you're really giving up the signal fidelity by adding these attenuators. So again, I just have a gas discharge tube, just like I show here. That's followed by pi type attenuator, again mine is 3 dB, followed by a TVS, again this is a very high speed part, low capacitance, and then that's followed by a DC block. In my case I'm using this 220 nanofarad part, again that's a 50 volt part, and this clamp here is going to clamp this front end much below this 50 volts. This part is never going to see anything near that unless this TVS were to fail open. And then again on the back side of this I have a 7 dB attenuator that goes off to the nano. This is looking inside of the unit. So you'll notice it's covered in dope. There's a couple of reasons you may want to consider using something like this. The first is obviously that it helps prevent high voltage breakdown. The other is that it acts as a sealer. Of course this stuff is toxic, it uses toluene, but of course the upside to this is it does work. Hopefully this will show up in the camera. This is our gas discharge tube right here. The 3 dB attenuator is located here. This is our TVS in the center. Here is our DC blocking capacitor, and then this is our 7 dB attenuator here. Again, this is all made out of 1206 packages, so fairly small. The idea with something like this, you could just mount this directly to your nano and just leave it in place. Again, if the only thing that you're using this for is looking at SWR, there really wouldn't be a reason to ever take this thing off. Alright, so you can see I've attached our little suppressor to the end of our cable. First thing we'll do is just load up a standard calibration. So again, we'll select 2-port cal, we'll select old, and we'll select 1 meg to 300 meg, 1-port SOLT. And now let's select transmission rectangular, and let's attach our through. And again, this is roughly a 10 dB attenuator. And there you go. So looks like it starts out at roughly 10.02, and it gets as low as about 10.5 or so dB. Fairly flat up to 300 megahertz. It's not very important because, again, the plan is to basically calibrate out any errors that this is going to create. So the way that we do that is we just run through a normal calibration. So again, to do that, we just select 2-port cal, we select new, and we apply the short to port 1. In this case, it's on the back side of our little suppressor. And we install our open. And we install our load. And then we're going to install our through. Again, we're working at fairly low frequencies, so I'm not going to take the time to torque these connectors. And we'll just store this over the top of our 1 to 300 megahertz single port SWR ESD. And you can see the unit now sees this through is essentially 0 dB. Let's go ahead and we'll install our 10 dB attenuator. Again, obviously not a metrology grade attenuator, but fairly close. And again, we can see a negative 10.08 is kind of where it starts off at. Looks like on the high end it's down at negative 10.2 or so dB. Fairly close. So let's go ahead and select standing wave ratio. Again, this is a 50 ohm system right now, so we can see our SWR is reading 1.01 or so to 1. Let's just try our 100 ohm resistor. Again, this should give us an SWR at 2 to 1. And you can see it's pretty close all the way from 1 meg to 300 megahertz. Let's just do a store 1. Let's try the same thing with our 200 ohm resistor. And you can see again, looks like 4.13 maybe on the high side, maybe on the low side about 3.8 to 1. Again, fairly close to 4 to 1. Very usable. Let's just try our 25 ohm resistor. Again, this is 24.9 ohms. Should be very close to 2 to 1. So pretty close. Here we have a 10 ohm resistor. This should give us a SWR of 5 to 1. Again, 10 ohms and 50 ohms. It's a 5 to 1 ratio. Looks pretty good. Let's turn off our memory so we can get a better look at this. Looks like 4.7 or so, 4.65, all the way up to maybe 5.1. I doubt there's many amateurs that are working 5 to 1 SWRs, but hey, this is a 1000 ohm resistor. Again, that should give us a 20 to 1 SWR. It's probably going to have some trouble with this. You can see we're 14.3 up to, what do we got on the high side? Maybe 23 to 1. So 1000 ohms is pushing this system pretty far, but again, it's probably not an area where most people are going to be using something like this. So let's reattach our 50 ohm resistor. And now again, let's save that to memory 1. Here I just have a short piece of semi-rigid. We'll attach this to the input side of our little suppressor. And we'll attach our ground for our little piezo. I don't know if the camera will pick this up. Let's just see. So that's an air discharge, probably an 1/8 of an inch. It's a pretty good arc there. Probably probably 3/8 of an inch. Let's try a direct. Now let's just reattach this to the Nano and let's see if that's had any effect on our measurement. So you can see it after, I don't know what, 10 different hits. Very little change in the actual data. It's probably had no effect on this. Again, the numbers that we used are fairly conservative. Of course, the proof is in the pudding, right? That's what they say. So here you go, totally attached to the Nano. Let's just try a air discharge. Again, we'll try this from about 1/4 of an inch away. There you go. And let's try a direct contact. Some pretty healthy hits right there. And as you can see, no effect really on the profile. So again, let's just try a different value on here. Again, here's our 1K ohm resistor. And let's just shut off our memory. And you can see, again, roughly 20 to 1 and about 14.7, 14.3 at the high side. I think that's what we saw before. Let's just have a look at the transmission. Again, we're expecting this to be 0 dB. Let's see. So transmission rectangular. And there you go. So 0.05 to 0.08. So hopefully this video gave you some idea how you could protect your Nano if you're making SWR measurements. Again, it wouldn't be very costly, and it's certainly not very difficult to come up with a circuit something like this. Again, maybe in your case just a couple of back-to-back Schottky diodes would be good enough. Here again we're demonstrating taking measurements all the way up to 300 megahertz and not really seeing any problems with it. So again, I wouldn't recommend that you do a test like this without some type of transient protection on the front end of this. I can pretty much guarantee you without this suppressor, one hit with this grill starter would probably wipe out this Nano. So there you go. Hope you enjoyed the video and found it useful. Till the next video, just stay safe. Later.